Gian-Marco Rignanese received his engineering degree in 1994, PhD in applied sciences in 1998 from the Université Catholique de Louvain, and then carried postdoctoral research at Berkeley with Professor Stephen Lowy, and is now a full professor at Louvain. He's also a research director at FNRS and an associate professor at the Northwestern Polytechnical University in Xi'an, China. So to conclude, he was named APS Fellow in the field of electronic structural calculation. So,
thank you very much for the nice introduction and for the invitation. It's really a pleasure to be here. We start to have covered a lot of things with the different talks, so I'll be saying a few things that have already been done, and maybe I'll bring some new things out. So we've seen, and Alejandro said that from the beginning, that a big deal of materials research still proceeds nowadays by trial and error, and here I bring the picture of Edison, that when he tried to identify the material to put in as the filament of the bulb lamp, he tested something like 3,000 materials, including the hairs of his assistant. And in the end, the material that he got was not tungsten, because he didn't simply try tungsten. So it took a few more years before we identified tungsten as the best material. So this is clearly a bias that we may have when we do these kind of things. And nowadays, we speak about paradigm of materials research, and I think that we are living right in the middle of the change of the paradigm. So in the past, we've been a lot of empirical science, then we have theory, and then computational science, from which a number of us are coming from. And then nowadays, we realize that machine learning is bringing some new way to analyze the data. This doesn't mean that the other ones are disappearing. They're always combining the different paradigms. So it's always important to do experiments like that. So the way we think about material science is this kind of these four things. So processing the materials to get a given structure. This structure will have some properties, and this will induce the performance of the material. And so what we try to do, one way is to try to establish relationships of cause and effect that a given processing will lead to the structure. The structure will have its properties, and the properties will lead to the performance. And machine learning can be seen as a way, and that's one thing that Alejandro was presenting, is that we can try to get the property as a function of the processing and the structure. Okay? But what we want to do also in the long run is to go the other way around, is to do the inverse design, that is trying to establish engineering relationships, that if I want to get a certain performance, what is the processing that I need to do, what is the structure that I will get, and what are the properties. So I'm coming more from, just like Sheping, from the directions of ab initio calculation, where we were used to work with a given structure and then make a property prediction. And so this is ab initio calculation. Of course, there, thanks, Sheping showed that, machine learning can bring something there by accelerating that, by getting data and then accelerating. The machine learning is the only way to do inverse design. So to do this thing, we need databases, and I will be speaking a bit about databases and about some work that we did around that. And so we can put ab initio calculation in the databases, but it's also very important that we gather data from experiment. And you as an institute, I think that having your own database where you share the data among you is something that I think is very important. So now, to explore this, this property space, there are essentially three ways that people have used. So one is the high-throughput virtual screening, just trying to search different materials. And it's a bit repeating what Edison has been doing, but doing that numerically, let's say. Then the other one, and I will say a few words about that, is global optimization. And then I touch to the last one, which is the generative model. So let me start with the virtual screening, and just, it was the talk of Alessandro that showed that. So the idea basically is that we, just like Edison, we take more materials, thousands to hundreds of thousands of compounds, and we compute a number of properties by using DFT calculation, for instance, and then I'll say how machine learning can accelerate that. And then so we compute the properties that the material need to meet in terms of requirement for a given application. And as you see, most of the materials that we try, they end up in the bin there, and there's only a few of them that make it through. And so basically you have at that stage something like 10 or 100 compounds that still need to be confirmed experimentally, okay? So to do these kind of things was necessary, and but we're doing quite a lot with PyMagen to that, to be able to do this high-throughput modeling, and so a number of tools that to be developed, workflow managers, and so on. And the other thing is, of course, the data mining. So as an example of what we have done in this field is some recent work that we did on high carrier lifetime defect tolerance solar absorbers. So you want materials for the solar panels, and you want to best one, and you want them to be with earth-abundant elements. And so typically the kind of work of funnel that you use there is computing the properties of the materials, and sometimes certain properties, as you can see here, for instance, the band gap appear here, but it appears here again, and you wonder why. Simply, if you look at the color of the border around the shapes, you see that there's a different color that relates to the accuracy of the calculation. And so when you want to deal with a lot of materials, you cannot be as accurate as you are when you have fewer materials. And so for instance, at the end, we can do things that are very demanding, like computing the intrinsic mobilities, which requires to compute the electron-phone coupling, which is very, very demanding, or even the capture cross-section. And we can also take into account things like this HHI index, which is the geographical spread of the elements on Earth. You don't want these elements to be only in one region. That's a bit like what Alessandro was mentioning about the cost of the material. This is things that can be included in the screening as well. Okay? And here the second color that you have, so you see that you want this HHI index to be very low, and then you want also something which is called the materials companionality that's actually related to the cost. It's the fact that when you extract the element from Earth, it can also lead to another element being obtained for free, basically. Okay? So this study that we started, I forgot to mention that, but if I go back, here we started this on a copper-based element, and we started with 8,000 compounds, and so of course at the end, the results that you get, you see they all include copper, because we started from copper, a bit like Edison, but then we tested tungsten. And so we extended the search to 40,000 inorganic compounds, and we found one which was very interesting and also not too expensive in terms of the elements that were available. And we did a good job there because we had some colleagues that were able to synthesize it and to test the different properties, and this is just being published in June. So we also applied this approach to a number of fields, and so here I just listed a number of those. So we have transparent magnetic materials, we have been looking for electrolytes, for materials for optics, and I'll get back to these optics materials later on. For ferromagnetic, thermoelectrics, multiphoric, you name it, and we were not obviously the only one to do that. There's actually been a huge number of people doing these kind of things, and you've probably seen appearing a number of databases, such as the Materials Project that Rignanese was mentioning just before, that have appeared online with a number of data that were available there. Each of them, unfortunately, had their own way to interrogate the database, and so you as a user of those databases, you would have to learn each of the way to interrogate these databases. And so we got together with all the developers of these databases, and we developed what is called Optimate, which is a specification that defines a unique way, it's an API that allows you to query all these databases with the same query, and you get a response which is of the same format. So just to show you, so we published this in scientific data. There is a number of tools that can help you to have your own database. So if you start adding even a little number, and I'll show you an example later on, even a little number of data, they may be useful to someone else in the world. So don't hesitate to share them, and this is an easy way to do that. So we are just about to release a second version with extensions to that, and you see that the number of people that are among the authors is growing simply because we have more and more databases, and actually Flipping was kind enough to have his Matterverse database be part of that. And As you can see here, so the kind of query that we have. So first, when you have a query, so there is a part here, which I didn't show here, which is the URL of your specific database. And from there, there's an endpoint that is common to all the databases. So there's the version of the API, then in this case, we're searching for structures. So this is a simple query to search for materials that are in group 14, okay? And so it's going to be N1 here, and you see all these databases give you a given number of answers. And as I was mentioning, some of them have a limited number of them. So for instance, this one, which is ODBX here, it's actually the database of one of my postdoc. And when he was a PhD, he had this small database. So the numbers that you have in parentheses here are the number of the first paper that I presented. The green one are from the new version of the paper. So you see that when he initially started the database, there were very little materials in it. But now this database has increased, and maybe they are useful to someone in the world. So let's make them available, okay? And so you can do things like querying for binary materials. You just have to add that you want 2 elements, and you can even focus on specific materials, so without lead, because maybe lead is toxic. And you see, you have all these queries, and you have a huge amount of results, which can be very beneficial also for training in the field of machine learning. So indeed, machine learning can be used with respect to this funneling approach, this virtual screening that I was showing, to accelerate the screening by obtaining, and that was one of the points that Schwepping indicated in the first place, that is that jump from the structure to the property. Okay? And as he was pointing, in the databases that we have, most of the data is about the easy to compute properties, because they take little time to compute. Properties like elasticity, piezoelectricity are much more demanding, and as he was pointing, the amount of data available in those databases is mainly about the easy one and way less about the other ones. And this is a problem also for machine learning, because the amount of data that you have is really crucial to obtain a good model. So when we take the easy machine learning approach, like random forest and stuff like that, you can quickly get a reasonable result, but at some stage your predictive power saturates. It saturates quite quickly, actually. But it's very interesting, as was pointed by Alejandro, that even with a limited number of data, you can start doing something. And especially for experimentalists, I think this is really important. As soon as you start to have even 20 data points, it's worth looking at that from a machine learning point of view to do active learning, as I will show you later on. So then, if you go to more complex approaches like neural network and graph network, you really need more data to get something that is better, but the accuracy for sure is improving. Okay, so you cannot beat the graph networks as long as you have enough data. So one of the things that we did in the first place, because often in our field the number of data is limited, we developed something which is called ModNet that is dealing with limited data sets, and it's also able to deal with several properties. Basically, the idea of working with several properties is that to try to find some kind of genome, a bit like the material genome indicated by Barack Obama, indeed, where we have something which is common to all the properties that we're trying to model. And this is MapBench, which is a benchmark where indeed there's a number of different databases. There's actually 13 different databases with 13 tasks. Some are regression and some are classifications. You have some that require to know the crystal structure, and some are based on the composition only. And then you have different sizes. And this is very interesting. Some are small data sets, and some are large data sets and different properties. So here at the top, so this is the mean average error on a logarithmic scale, with at the top the dummy. So that's something that basically tosses a coin and gives the results. So you really need to beat them to get the results. And so the lower you are in this table, the better you are. And so ModNet is working quite well for the tasks that are with a limited amount of data, so we're actually leading for tasks. But as soon as there is a large number of data, things like M3GNet or other convolutional graph network take the lead. Okay? Then I'm coming also to a point that Schwepping was showing. I think that gathering data, they will always have different accuracy. And so it's really important for me to work in the direction of the multiplicity. So I actually reworked after Schwepping had done his work. We actually tried a different approach in our case. So what we did was to to try to denoise the data. So the idea is the following: we put all the data together, and here basically the colors that you have is different functional. So you have PBE, HSE, and so on, the same as basically as Schripping was showing. And so the first approach was to put them together and to train on one, then another, then another, and then another. It's what is called curriculum learning. So when you go to school, you have to learn at first the addition, then the subtraction, then the multiplication. You could change the order. The results are going to be very different. Okay? And so this is what we tested here, which is the one-by-one approach that we go. And then we tried another one, which what we call the onion approach, where basically we learned all of the things together. So continuing with Marazoni school, you would learn all the operations together, and then at some stage you remove one, then you remove another one, and you remove another one. Okay? So this is what we do here. We learn all the data together, and we try to see what's the best model with that. Okay? It turns out that the onion approach is the best one. Okay? And it turns out that the order, so the curriculum that you have to follow, is starting from, so in the case of the onion, so we put all of them together, and then we remove one after the other, the ones that are less accurate. Okay? And so this also kind of answers one of the questions, the last question that you asked. Basically, the idea is that you don't know the quality of the data in the beginning. Okay? But at some stage you have to say, okay, these I trust them. You really need to have that because the machine cannot do that for you. You need, as a human, to decide, this is what I trust the most. This is important. But once you have that, you can compare the other ones to that, and that helps to find the cases that are problematic. So once we have this model that is able to predict things, we apply this denoising approach. So basically we have a number of structures for which we have the property, okay? And so we have different prediction of that property. So that's the PBE, the HSE, the experiment, and so on. And so there's one that we need to say, okay, this is the good one. So in our case, we chose the experimental one. And so with this model, basically we can make predictions for each of these structures. And so we decide that based on this prediction, we're going to define a threshold that if one of the previous predictions falls outside the threshold, we correct that by the new value. Okay? So basically we change that to this one. Okay? So anything that is outside this prediction that we consider to be okay, then it's correct, is denoised. Okay? And that's what we do, and you can of course do that for all the structures. You get a new data set, and you can train again your model based on the new data that you have, so you can do that several times if you want. But we noted that after one or two iterations, we kind of converged over. Okay? And so thanks to that, there's the animation here. Yeah. So thanks to that, so the purple result is the result of Schripping, okay, which were very nice indeed, where showed that indeed it's important to gather all these data to take the most of it. And here we managed to get something, so the red ones, which is even better than any DFT calculation. Okay? So the orange is a scale DFT because people know that DFT was underestimating, so they did some trend and they rescaled the data that they had. Okay? And so now there is a way, thanks to the amount of data, this is why I insist on the multiplicativity. I really appreciated the work that Schripping started on that. Because we're going to live in a world like that, where you have to deal with the fact that other people have done the measurements, you do your own measurement, of course you trust yours more than the other, and so you want to take the most out of that, and the amount of data is really crucial, and so multi-fidelity for me is one way to go. I'm not saying that what we are suggesting here is the best way, but I think that is something that we still need to explore. So as was clearly shown in the previous talk, I think that machine learning is also a way to bridge the scales of length and time that can be simulated. I'm not going to say more about that because High-Throughput and Schripping talked about that before. Maybe I can push in the direction that Schripping was mentioning, so that this universal force field have improved things, but we are already now moving in the direction one step further, because he was mentioning the fact that these force fields, they can predict some properties like the Von-Dose center, but there are some properties that really require to have the access to the electronic properties. And one of the steps in the direction is the fact that now people are starting to build machine learned Hamiltonian that can give you access to the property to a certain level, okay? And even in that field, we have now seen the fact that there starts to be universal machine learning. It's just a question of the amount of data that you gather, and now we'll be able to have a prediction of the Hamiltonian for any given system. Okay? And of course, it's going to be imprecise, but again, in terms of screening things, it's going to be very useful. So let me move to the global optimization here. So basically, this is an example that we did and that we are about to publish. So we've been looking in the past for materials that require a high refractive index and a high band gap. I'm not going to spend too much time on that. Basically, a few years ago, we computed a high-throughput calculation on DFPT, so that's very demanding calculations, on 4,000 material. Okay? And at the time, we studied that from the physical point of view, and we managed to get a model explaining the underlying physics to make it simple and to try to see what was important. Another thing that we did with ModNet, and I think is very important, is to we developed a probabilistic model. So basically, it not only gives you the prediction, but it also gives you an error bar. The way we do it is by bootstrapping. So we have different models that are generated at the same time, and so you have several predictions, so that you have the mean prediction, and then you have a standard deviation for each of the predictions. And this allows you to do Bayesian optimization. So the idea of Bayesian optimization is that if you have a given function that you try to minimize or optimize, you know it at certain points, and in between there is an uncertainty, so you know it precisely there. And so what you try to do is that you try to predict what is the next, in this case, DFT attempt, but it can be any experimental that you want to do next. In experiment, and I have some experience collaborating with experimentalists where we do this approach of active learning, where they have a number of experiments and then we suggest what is the next experiment they should do. This is really effective, I bet. And so the idea is that through an acquisition function, you decide what is the next best experiment. In this case, that's a DFT. So this is the way the circle works. So we have a number of data, we train a model. From this model, we decide what is the next things that we're going to measure. We then do the measurements, and once we've done the measurement, we add the data to the training data, and we continue the loop. So basically, in the example that I have here, we try to push the curve. You see that the refractive index basically decreases when the band gap increases, and so we'd like to push the Pareto front that you have there upwards. Okay. So this the idea. Can we move in the upper right direction there? Okay. So to do that, we use ModNet as the machine learning model, but you could use random forest, whatever. It's not really important, especially initially, especially in the cases where you have a limited number of data. And the ModNet allows us to predict new candidates. So basically, the way we do it here is we look at the different databases that are available with Optimate that I was mentioning to you, and out of these, we apply our machine learning model to all these databases. It's a huge amount of data. Don't care because it's machine learning, it's fast. And so you can make prediction and compare. So you then take the most promising ones, you do the DFPT calculation, and you compare to that, and you see that the agreement is already nice. And so starting from something where we started from the materials project, we applied our machine learning model to the whole materials project. You see that the error bars here are quite big in the first step. And we selected the number of materials C, and we computed the DFPT with that, and you see that they are all falling close to the Pareto front and pushing it a bit forward. And so that's the second step, and so on and so forth, until we reach a moment where we see, so this is the original errors on the error bars on the materials project. So when we manage to get something small, we move to another database, Alexandria, which is developed by a Portuguese guy, actually, who is in Germany. But we have access to all these data through Optimate, and so we applied it again there, and you see that in the end we have something which is very nice and really can be at the Pareto front. Okay? Yeah, this is just to show you that how close we push the things. Okay, so I'm going to finish by saying a few words about the generative model, basically. So the idea there is that we want to go in the other direction, and I would like to make an analogy with what people have been doing with pictures. So that's where generative AI has been the most effective. And so basically what people do there is that there's so many pictures in the world that they've been able to identify what is called a latent space. So it's a space of small dimension that contains all the information about these pictures. And so if you move in that space, you can go wherever you want. And so in practice, what they did mean, here it's an oversimplification in the sense that this latent space is represented as being two-dimensional. That's clearly not the case, but that makes it easier to see it this way. So in this latent space, they put all the points that they label as women and all the points that they label as men. And as a result, they are able to identify a direction that increases or decreases the femininity of the face, okay? And so basically they're able to change a woman's face into a man's face, or the other way around in a kind of continuous way, okay? And we as material scientists, it would be ideal if we could find this latent space of material and identify directions that are related to some properties and be able to tune the property in the way we want, okay? And we could identify also reasons why. I mean, in the plot that I was showing you about the refractive index as a function of the band gap, why we're limited there and we cannot push the Pareto front too high in that direction. There must be there something that we can explain from this latent space probably, but I don't know how yet. Okay, so there's been a number of things that have been done in terms of generative AI for materials. A lot in chemistry and molecules, as I was saying. In the field of inorganic compounds that are periodic, there's way less. The most promising one that I've seen recently is this paper where they define this method, which is slices. And what I think that is very interesting here is that they have a reconstruction rate. So basically, once you have defined this latent space, you can go back, you can invert. We were discussing before for one of the papers there about the inversion of the representation that you have. This is really crucial. It's important to be able that if you have something that works, be able to say, oh, what is the material that's beyond it? Or even if you think about the experimental ways, what are the processing parameters that give me that material? Okay? And in this case, they have a reconstruction rate of 95%, which is very promising. So I think that I showed you that materials informatics can help to discover materials with very specific properties. And I thank you for your attention. I would like to thank my collaborators on this, including Shruti, with whom we had a lot of conversation at some stages. Thank you very much.
Rignanese for this very nice talk again. The floor is open for questions, please. One question.
Gian-Marco, very nice talk. I have two questions actually. So the first one is regarding the denoising algorithm. Which of the data sets did you find have the largest noise and adjustments, right? Is it the experimental data, the HSE data?
No, the experimental one is supposed to be the true value.
So then I guess PDE is the largest noise.
Exactly. Actually, that's not completely true. There was one which is the GLLB.
So GLLB has even higher.
But the reason why it's because it's a bias set. So people develop, the data set that you have. So when we develop a new functional, people test it for a kind of material. They didn't test it for metals. So PDE is nice because they have. If you look, so one of the things that we did in this work is to look at the distribution of the data. So the data set in PDE is basically half metals and half non-metals with a wide and high band gap. In the GLLB data set, there were no metals. So that one was kind of biased.
I think the HSE one as well. So I think those two data sets.
Maybe the HSE, actually, I mean, the accuracy, the average accuracy of the PDE and the HSE were very similar, just because the PDE was good at predicting the metals.
The other question I have is regarding the latent space for generative AI for material science. So conceptually, I mean, the simplest latent space we can come up with is composition, both in terms of swapping elements as well as in terms of tweaking the ratio, right? My concern is always that changing relative composition ratios is continuous space, roughly speaking. But swapping elements is discrete space, right? Because changing lithium to sodium or lithium to magnesium is a one-step jump in multiple different properties. We don't have complete flexibility in tweaking properties in a continuous manner, right? So, how do you think that should be handled in the generative AI?
I still don't know how we will end it, but a step in that direction. Maybe you've seen there's a work by Michele Ceriotti where he is looking at alloys, okay? And he was able to show that the element of the periodic table, okay, that he was considering, he could recreate each of the elements as a combination of 4 or 5 different ones. So, which he termed, air, fire, wind, air, fire, water, and so on. By mixing them, he was able to reproduce the properties. So maybe there's a way in that direction that there are some basic components that we still don't know at this stage. Okay, some basic components that could recreate the different elements and swapping them. But also you can think. You can try to introduce some continuity if you increase the size of the supercell. You make a supercell, and then you have these partial occupation of the sites that could bring something that is an in-between 2 elements in the end. So I still don't know, I don't have a final answer, but these are the directions that I would explore.
Okay, we have time for a few more questions. Please, from the audience. So I have one question about this active learning loop and the relation with the experimentalists.
Yes.
So the reaction time of an experimentalist is certainly not the same as someone that does, I would say, typical computation.
Yes.
So in your experience, how much was this time response a factor in the work that you've done?
I mean, it's the limiting factor. That's clear. I mean, so depending on the experiment that you have, it can be like a few weeks or even months. I mean, sometimes doing the required experiment can take some time. But if you're lucky enough, so I actually have 2 experiments. I can show some results if we have time. But, you want to do that? Yeah. Okay. So I'll do that. Okay, so basically this was a work where we're looking at electrochromic properties of tungsten oxide materials. So basically people want to make them transparent or non-transparent by applying a switch. It's like windows that you can decide to be transparent or not. And so they wanted the materials to remain, so it becomes blue when you apply this electric field. They wanted to remain blue more than 48 hours, okay? So basically they gave us a number of data. So there's a number of parameters that enter into the process of creating the material. And so they wanted us to increase the time that that the material remains blue. And so we defined some score of persistence, okay? And so out of these 12, so that's not very many, you could establish a map that could tell them, okay, if you change your process parameter in this way, you should increase the persistence, okay? And so in this case, we gave them 2 new predictions, okay? And when they applied it, you see that we managed to get a persistence of 93 and 94. But it was bad because actually they realized that they could not go back to the transparent state, okay? So we say, okay, well, then we need to define a reversibility score as well, okay? And so we now have 2 scores that we combined, and we could define a global score, combining everything, and again, provide them a map of where to go. But you're right that in that case, it's always the limiting step is the experiment in the end. But I mean, really, the approach of it reduces the number of experiments that you need to do annually. This is really, and we have another project, so the paper is submitted, so I cannot show it here, but we have another project where we clearly help the experimentalists go in a very good direction.
Okay, so we thank, if there are no more questions from the audience, we thank again. And in this critical time, I would like to tell everyone that lunch is served upstairs. There are stairs to your left when you exit the room. So, and we meet after lunch for the afternoon sessions.